Hello everyone, and welcome to another SuncatByte. In this SuncatByte, we're going to talk about data variables and memory. So to this point, we haven't really talked about memory when it comes to our variables. We've been declaring variables. Variables have had a name, then they've had a value. But in reality, when a variable is declared in a program or in C++ in general, or in C++ and in general in a program, when a variable is declared, the physical memory in RAM is reserved for the variable. And then the number of bytes that are reserved actually depends on the type of variable. So when you look at a variable, this table here actually illustrates in C++ what the bytes of memory are that are reserved, or typical bytes of memory that are reserved. So for a char, we get 1 byte of memory. Remember, 8 bits in a byte. And in that, you can represent -128 to 127. So you can represent that many different characters that range from -128 to 127. Unsigned char is 0 to 255. If you look at an int is, what is that? -2, 147, 483, 648. 2, 2, 147, 483, 647. Then you have a short int, you have an unsigned int. If you look at the unsigned int, notice it starts at 0, so you get more positive values. Notice a float takes 4 bytes. Notice how many bytes a double takes, which is 8. That is double 4. That's where it comes from. That's where the name double comes from, right? So every time a variable is declared, we have to reserve that much memory inside of RAM, or random access memory. If for some reason you want to know how much memory a variable takes up, C++ has this pretty cool little operator called the size of operator. And that'll return the number of bytes reserved for either a data type or a variable. So if you say size of and then a variable name, or size of and then a data type, like this in the general format, then you'll get how much memory is used by that, or reserved for that variable in this case, or that data type in this case. So if you say size of int, you should get 4, right? Because it's going to reserve that much memory, that many bytes. Okay, so the thing you need to keep in mind though is the computer reserves actual memory locations for program variables. Let's look at a few different things. So first off, the computer reserves actual memory locations for variables, program variables. Memory locations are addressed, period. They have an address. The variables declared are placed on what is variables are placed on the stack. That's a part of memory where the variables are placed. The first variable is placed at the far end of the stack, the first variable declared, and then the last is placed at the beginning. Okay, so because of this, that first variable has the highest address. So if we look at this figure, which is off the screen, let's see here. Let's adjust this guy. There we go. So if we look at this figure here, it shows where the variables are declared and on the stack. So in this case, say that you're looking at the stack starting on the right, the first variable declared, which is x, right here, See, there's the float X statement that declares it. It's here at the far end. It's a float, so it takes 4 bytes. Then Y is next, so that gets declared here. Then I and then J, I, J. Notice those are also 4 bytes. Q is a double, so it's 8. R is a double, so it's 8. So that's the bytes of memory. It has an address. We haven't looked into the details of an address yet, but we will later on. So that's one way to look at it. You can look at it this way as well. A stack, like it's a stack of newspapers. The one you put on the bottom is here. The one you put first is on the bottom, so X, just like that, X. Then as you go up the stack, you get the other variables. Okay, so when we look at computer memory, boy, this is just like totally messed up with these bullet points. Huh? Okay, here we go. So when we look at computer memory, we need to know that sorry about that. So we look at memory. Okay, I'm just not going to do this anymore with those. So when you're looking at computer memory, it's addressed by hexadecimal notation. Okay, and hexadecimal numbers will look something like this. So hexadecimal is it's a numbering system that accounts for 16 different values, 0 through 9, and then 8 through F. So that's why you see a mix of numbers and letters. And each of these addresses in hexadecimal notation is 4 bytes long. Okay, so then looking back at a figure that adds another element to things, which is an address, similar to what we looked at before. Here's this figure. It has a bunch of addresses in it. It has a bunch of variables in it. The same ones we saw before. Float X, Y, I, J, Q, R. Notice they're declared on the stack. Now, the other thing to notice is they have an address. The address here is 0x0066FDF4. This one has the same beginning part and it's FDF0. This is bigger than this. This address is bigger, 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 bigger. Then here's the other parts of the address. So F4, F5, F6, F7. Okay? So the thing to really think about there is that we now have an address. Before we were basically just looking at a value, right? Now we're not looking at just a value. There's other parts to the variable in addition to the value. Okay, so what are those things? Besides the value, every variable has a data type, a name, a value, and an address. And then the data type will also have a size. So you can think that there's 5 different things, right? A data type, a name, a value, an address, and then the size, which is based on the data type. And now we know how those addresses are actually assigned, or actually what they actually look like with the hexadecimal values. So then say we do some assignment statements like this. If we do some assignment statements, then here's what happens, right? Things were already declared. They had an address. As soon as we say x equals 1, we get 1.00 here. Then if we say y equals 2, we get 2.00 here. Say we said j equals 4 first. Then actually this would stay blank here where I is, and then j would get 4. Then if I was equal to 3 was the next statement, we'd have 3 there. Here we just did everything in order, right? X, Y, I, J, Q, R. So remember that there isn't a value assigned until you actually use the assignment operator. All right, so that's it on data variables in memory. Key thing is to remember that they have hex addresses, and then variables have all these characteristics. They are these characteristics. They have a data type, a name, a value, and an address, and then with the data type, it has a size. We can use the size of operator to look at that. So let's actually look at the size of operator, an example of the size of operator here. So if we look at program 5.1, you can see that we declared a bunch of variables up here: char C, double D, float F, int I, and long L. Here we say size of, and then the variable names, C, D, F, I, L. Remember, from our notes, we can do size of with the variable name, or we can do size of with the data type. Right now we're dealing with the variable name. So, given this, and given this table that we saw in the notes, what should we expect to see? So with the size of, with the char, we should see 1, right? A float, or double, we should see 8. A float, we should see 4. And int, we should see 4. And a long, we should see, where's our long int? Right here, 4. So let's see if that's what we see. So let's see if that's what we see. So we go ahead and run the program. Go back to our chart. Here, so we had a char is 1. That matches our chart. A double is 8 there. A float is 4 there. An int is 4. Regular int is 4. Long int is 4. So there you go. The size of operator matches. That's it for this SuncatByte. If you have any questions, comments, or concerns, please do let me know via the discussion board forum, email, or during office or lab hours. Until then, take care. Bye.